Yeah. Okay, so are we being recorded? Yeah, okay. All right, so the drop deadline passed, and it looks like we have the final count is 12 students in the course. So that's also roughly, what I guess what we expected given the attendance the last couple live meetings. It was around 12-ish. Plus, I know there were at least 2 auditors that showed up. So yeah. So assuming 12 students is the final count and every student presents twice, we'll have 24 student presentations in total. After today, we will have had 3. So if we budget for 7 more live meetings, then we will have 3 in each one of those. That way we can leave some room at the end for final project presentations. We'll see if we need to use up all that room or not. Potentially, in order to save time, potentially I'll ask everyone to pre-record their project presentations. Just do a 10-minute presentation and share it on Dropbox or something, and then have everybody watch those and meet only once, kind of for general discussion. So we might do that in order to save some time on the presentations at the end. We will have to start talking about the project sooner or later. I guess not quite yet though. So maybe we'll mention a few things about it next week. Right. So before we get to today's presentations, just so people know, it is QIP this week. This is the Quantum Information Processing Conference. You're all welcome to attend it. I mean, it is online. I think it's registration is registration free? I think it was free. You should look at the schedule. Maybe I'll post a link here and check out if there's any interesting talks that you want to go to. Let me just put the link. Hold on a second. Okay. Okay, so this is the link in the chat. If you go to either the program, if you go to the conference program, then you can download the list of all talks, or just scroll down to see the schedule. But I mean, I guess it's more convenient to download the PDF of the schedule, and then you can kind of see if there's any talks that interest you. So there should be a fair number of talks that are relevant to this course, but I won't make everybody go to everything. Also, they should be recorded, the talks. So I'm not sure exactly what the plan is for kind of posting the recorded versions, but I assume that will be done or has been done, and I just haven't found it yet. Still, if you're interested in this field, I do recommend going to at least parts of this conference. So right, that's one thing. Another thing is okay. So maybe after today's presentations, we will talk about next week's reading assignment and ask for volunteers. Okay, and so since there are only 9 attendees, okay, but looks like the auditors are not here. So is that right? Okay, so maybe it's so okay. So it looks like 8 students are here right now. And so we sometimes last week we had like 14 because there's sort of 12 students and 2 auditors that I know about. So we may have to assign some people to present who are not present, depending on if we have enough volunteers. Okay, so who wants to start us out for today's presentations?
I guess it makes sense for my paper to go first.
Okay.
Yeah.
I guess that makes sense. Yeah. So go ahead, Abhishek.
Yeah. I'll just start sharing my screen. Can everybody see my screen?
Yeah, I can see it.
Yep. Okay. So essentially, what this paper does is that it proves an exponential separation between one-way quantum communication and two-way classical communication. So I guess we haven't formally defined one-way versus two-way in the lecture yet. So, but it seems pretty straightforward. In two-way communication, both Alice can talk to Bob and Bob can talk to Alice, so they can exchange bits between each other. While in one way, only one of the participants is allowed to send bits to the other participant. So just for without loss of generality, only Alice is allowed to send bits to Bob. So before this paper came out, there were 3 results that were known in separations between quantum communication complexity and randomized communication complexity. The first one was by Raz in 99, which showed that there's an exponential separation between quantum two-way protocols and randomized two-way protocols. And the function that this paper uses is actually very, very similar to the function that we will be seeing later on. And then in 2007, it was shown the same thing holds even for the one-way case. So quantum one-way protocols are exponentially um, better than randomized one-way protocols. However, the function that they used was easily solvable using a classical two-way protocol. So this does not give us a separation between one-way quantum and two-way classical. And finally, in 2008, there was a result that showed that for a relational function, so not like a the kind of functions, not like a decision function, there was a separation between an exponential separation between quantum one-way functions, quantum one-way protocols, and randomized two-way protocols. So I guess what this paper mainly did was that it proved this last statement, but for a decision problem and not for a relational problem. So the main results is that there exists a function for which there is a quantum one-way protocol, uh, which uses exponentially less number of qubits compared to the bits used by a randomized two-way protocol. So the problem that they deal with is actually the complete problem for one-way quantum protocols, and they call it the vector and subspace problem. And uh, it's basically so Alice gets a unit vector in, let's say, Rn, and Bob gets 2 perpendicular subspaces of dimension n by 2, and we can just assume that n is even just to make things nicer. And and this is a promise problem, and we know that the distance between this unit vector and one of these subspaces is really small. So, for example, in the case where n is 2, so just in the 2D case, we can sort of assume that the x-axis is h0 and the y-axis is h1. And we know that x is actually coming from this cone, the red cone, or the blue cone. And what we really need to output, what Alice and Bob need to compute, is whether x belongs to the red cone or to the blue cone. There's one caveat because in all of our, this seems to be an infinite dimensional problem because x can have infinite domain, but we basically restrict it to we basically allow only polynomial precision. So we allow log n bits to store each real number. And it can actually be easily seen that both these problems would have similar communication complexity. So for example, if you want to solve the non-precision problem, all we can do is we can just find the closest precision input and then just solve precision VSP. And precision VSP is just a restriction of VSP. So we already know that it would have at most complexity VSP. So by these arguments, we can sort of see that just by proving things about VSP, we prove things about precision VSP. And yeah, so the quantum protocol is pretty straightforward. Alice sends X, which is let's say it's a n bit vector, so we can encode X in log n qubits. Then Bob just does a measurement. So these are perpendicular subspaces. So it's a standard quantum measurement. And because of the promise, we know that it's either close to H0 or H1. We know that this would succeed with high probability. And we can set the parameters so that the probability is greater than half. And so this succeeds in log n qubits. So the quantum protocol is pretty straightforward. And then in the classical protocol, which is where what the bulk of the paper deals with, is actually trying to prove that any two-way, even if you allow two-way communication, any classical protocol would require at least n to the 1/3 bits of communication. An algorithm is known, it seems, for square root of n. So it's conjectured that this might be able to be improved to square root of n, but this is what they prove in the paper. And that's, yeah. So that's basically the main. I can start sharing the paper, I guess, if people have questions.
Okay. Okay. Any questions about this paper by other students? Anybody else who kind of looked through it and had any comments on it?
This isn't really a question, but I just remember reading it and being amazed at how perfectly this problem fit into like a quantum way of thinking about it, and how simple the quantum protocol for it was. I just remember like this problem seems perfectly designed for this sort of thing.
Yeah. So turns out this problem is actually a complete problem for all one-way quantum communication. So you can literally take any protocol and just do a reduction. So it seems natural that this would probably be the problem where we would get an advantage. We would get a separation.
Yeah. So I mean, right. In some sense, because it's a complete problem for one-way communication. So I guess it means anything you can do with a quantum protocol, you can basically do simply by kind of reducing it to this specific problem, at least for one-way communication. So yeah, then it kind of implies that if there is a separation of this type, then it should be there should also be a separation for this function. Of course, proving it is the hard part to the classical lower bound. So I should mention, I guess, so here we have a separation between quantum one-way and classical two-way. So it's a bit of a weird thing to do. So if you think about well, okay, if you think about communication complexity in general, then it should be clear that two-way communication is always faster than one-way communication, in the sense that you need to exchange less bits if Alice and Bob can talk to each other interactively and go back and forth. Then they need to exchange less bits to compute the function, a function on their inputs, than if only Alice can talk to Bob. So here we have a situation where only Alice can talk to Bob, and you know, it's a very restricted setting. in a sense, Alice basically has to send her input. Not quite, because maybe she doesn't have to tell Bob everything about her input in order to compute f of xy. And here in particular, there's a quantum protocol where Alice doesn't send her input, and instead she puts her input in the amplitudes of a superposition and sends that quantum state, which is basically exponentially smaller. So normally this separation is not very good. I mean, if you take any n-bit string and try to put it as the amplitude of a log n sized quantum state, I mean, you can do that, but you won't be able to extract those n bits again. I mean, those n bits, this encoding is not very useful for doing things with those n bits, except for doing this specific problem, except for solving this vector in subspace problem. It turns out. So it's kind of almost the only thing you can do by encoding an n-bit string in the amplitudes of a log n-bit quantum state. Remember, amplitudes should sort of be thought of as square roots of probabilities. It would be very strange to say, oh, we'll encode an n-bit string in, the probabilities in a distribution over strings over log n bits, right? So it's a very strange encoding for an n-bit string, and it's not a very useful encoding because sort of in practice, if you transmit probability distribution over log n bit strings, then in practice the other player will just literally see one of them, and that's like seeing a single random bit of your n bit string. So just seeing a random, like the index of a random one within your string or something like that. So it's basically it feels like a very weak, inefficient, not very useful encoding, and yet the quantum version of it does let you do something that you cannot do classically, and that something is exactly this vector and subspace problem. And again, the point here is that they proved that even classical two-way communication requires exponentially more time, so it requires n to the 1/3 instead of log n communication. So even if Alice and Bob talk to each other back and forth, they just there's nothing they can do to get anywhere close to this quantum protocol. So it's a kind of remarkable demonstration of the power of this quantum, I guess this particular quantum encoding scheme, but just quantum computation in general. That so sort of as a general guideline, putting information in the amplitudes of a quantum state is not very good. You won't be able to extract that information back again. There's very little you can do with that information later. But there's some exceptions, and this is one big exception. You can solve the vector and subspace problem if you do that. If you put information in the amplitudes of a quantum state. So I should also mention about this paper that suppose you just wanted a normal separation between two-way quantum communication and two-way classical communication for partial functions. So this is a weaker result, right? So you only here they have a two-way an exponential separation between one-way quantum. This is a weak quantum model. They show that this weak quantum model beats a strong classical model. They show it beats the two-way classical. So if you wanted a weaker result, which just says that two-way quantum beats two-way classical, also for partial functions, then first of all, this was done in '99, so it's kind of an old result that I didn't make you guys. I didn't feel like making people read because it's sort of outdated now. But also, there's more modern techniques. More modern technique would be to basically take a query separation. So, for example, Shor's algorithm for period finding. So take a problem like period finding that has an exponential separation in query complexity, and then basically lift it by composing it with a small communication gadget. So I briefly talked about it in the notes, but so you can take any query function and compose it with a small communication gadget, and it turns into a communication function. And this communication function can be computed in its most, the query complexity of computing the original query function times some cost of computing the gadget times some log factors. If the gadget is small, then this is basically saying the communication complexity of the new task will be at most the communication complexity of the old task. And so all that remains to show is to prove a lower bound. And this was done recently, like maybe 3 years ago, for classical communication complexity. So it was shown that if you take a query function and compose it with a small gadget, the two-way classical communication complexity of the resulting communication function is at least the classical query complexity, the randomized query complexity of the original query function. So I guess the upshot of all this is that if you just take period finding and you compose it with a small gadget, then it becomes some communication function, some weird communication function that must have the property that it's still exponentially slower to compute classically than it is to compute quantumly. So that the quantum communication complexity of the new function might grow to like log n because we lose log factors, but the classical cannot decrease below what it was except by log factors, and it started out being whatever it was, n to the 1/4 or something for period finding. So this would give you a separation between two-way quantum communication and two-way classical communication, and that would be kind of a more modern way of doing it. Why modern? Because basically this lifting theorem for classical communication complexity was only shown like 2 or 3 years ago, and it's required to get this to work. So so there's some context for this result. So this result does the stronger thing of separating a weaker quantum model, a one-way quantum communication, from the stronger classical model. Okay, any other questions or comments on this paper? All right. Okay, well, thanks, Abhishek. So I guess in this case, let's do the other paper by Andrew.
Mm-hmm.
Yeah.
So I warned my laptop is very old, so we'll see how well it handles sharing the screen while presenting. But hopefully it should be fine. It's not pulling up the options for sharing my screen.
Oh, do I need to approve you or something? Or
well, it just pulls it up and loads it for a while.
Okay.
All right, so sadly I can't. It looks like it's not going to allow me to share my screen. But I can hopefully just present everything in words. It shouldn't be too bad.
Okay.
Okay, so I guess I'll begin. Gavin was brought up in Abhishek's paper, and in relation to his old result in 2008, showing a separation between relational problems. So the first thing that they go over in the introduction is a brief hierarchy of the types of problems. And the hierarchy goes from total functions, which are the strongest results, to partial functions, which are in the middle. It's kind of our bread and butter for this course. and then to relations, which are the weakest results, but the easiest to obtain. And I guess kind of the logic there is that relations are, imposing basically no constraints. But a function ensures that, for every input, there's exactly one output. And then a total function applies this extra constraint that, every input must be defined. So essentially, the more restrictions you put on it, the harder it becomes to come up with these results. But again, for this paper, this is going to be a partial functions result. And he's working in the quantum simultaneous messages protocol. So what that means, it's a little bit different. The easiest way I thought about it was in the course notes for this week, we talked about the formalism for the deterministic communication complexity, where there is a referee that Alice and Bob are both communicating with. And in the simultaneous messages protocol, there's a referee, but that communication is one way. Alice and Bob can communicate with the referee, but the referee can't communicate back. And that's why it's called simultaneous messages, because theoretically they could send these two at the same time, these messages. There's no like back and forth anywhere in it. And then quantum, technically, Gabinski even makes in other papers, makes the distinction between quantum and quantum classical, depending on whether Alice and Bob can send quantum states, etc. But in this case, they both have access to one, shared entanglement to begin the problem, and two, they can send quantum states to the referee. So the problem that Gabinski uses for this is a little bit more complicated. Sadly, it's not as natural as the complete problem, the VSP. But in this case, he calls it the shape problem, the shifted approximate equality. And what it basically means is Alice receives two bit strings, x1 and x2, and Bob receives two bit strings, y1 and y2. And the question is there a cyclic shift of x1 and y1, right? So if you shift them by the same index I, does there exist an I such that when you shift them and then you XOR all 4 bit strings, x1, or the shift of x1 plus x2 plus the shift of y1 plus y2, is that close to 0, right? Or is the Hamming weight of it, the number of ones that show up in that XOR, is that close to 0? And by close to 0, they mean 6n over 15. And you're given the promise that either it's close to 0 or it's close to half of them. It's close to between 7n over 15 and 8n over 15 that are 1. So you're given this promise that either, for every single shift, this weight is close to half of what it could be, or there exists some shift where this weight is low. And to solve this problem, Gabinski reduces this to another problem called shape I. And what that is just you fix the index I. Right? So it's not that complicated. It's just imagine you don't have control over what the cyclic shift is. Is it still true? But so this reduction isn't really like a natural thing to think of, because if Alice and Bob could solve shape I, then they would have to send like n copies to solve shape 1, shape 2, up to shape n to convince the referee. But if you can make sure that Alice and Bob are able to solve it independent of I without even knowing I, then they only have to send one result, and the referee can just do n different checks on it, right? But those n checks also all have to kind of, you can't destroy with the measurements, you can't destroy the state as you go. So the projections, the productive measurements that the referee is going to be performing have to be able to go one after the other without destroying the state. So the way that they solve this is essentially, sadly I can't show this because it's a little bit easier to show on the screen. But essentially, they're just given, Alice and Bob are given two quantum states, like the A register and the B register, and rather the state A and the state B. And the state A is split up into two registers. The first one is held by Alice, the second one is held by Bob. And similarly, the second state, first register held by Alice, second register held by Bob. So this is the shared entanglement that they start with. And it's just set to like kind of the canonical entangled state. It's a equal superposition with no phases of 1 up to n. And if you're working with qubits, you can do this just by applying like an n-fold Hadamard. If you're not working with qubits, then the quantum Fourier transform applied to the state 0 will get you there. But essentially, so they're just given this kind of canonical entangled state, And what they do is they apply phases that correspond to the non-zero bits of x1, x2, y1, and y2. And because these states are entangled, when you apply those, even though they're applying to separate registers, those -1 to whatever power factors get pulled out front of the state. So now you have a sum over some, superposition with all these phases thrown in. And then they send all of their states to the referee, who just applies a backwards cyclic shift on the states, which then applies a forward cyclic shift in the exponent of the -1. And then from there, he just measures. And you can, he doesn't measure. He performs what's called the swap test. Now, the swap test, for anyone who hasn't done quantum algorithms before, I've noticed that it shows up a lot. And it's this pretty simple protocol where you just start with two states, phi and psi, and some state that's initialized to 0. And all you do is you apply Hadamard on the 0 state, and then a controlled swap operation, right? So when that state is 0, which happens, half the time because you've applied a Hadamard to it, you keep it, phi and psi in the correct order. And when state's 1, you swap them. So it's psi, then phi. And then you apply another Hadamard and measure. And it turns out that when you measure, you get something which is proportional to the square of the inner product of these two states, phi and psi. So it's 1/2 plus 1/2 of this inner product squared. And what that means is if these states are orthogonal, right, they have inner product 0, then you get 0 half the time, you get 1 half the time. Right? It doesn't really tell you anything. But if they're equal, or even close to being equal, then your probability of measuring 0 is very close to 1. So that means that you can distinguish between states which are, have an inner product close to 0 or an inner product close to 1. And what Gawinski is able to show is when you take the inner product of these two registers, the A and the B, when the referee takes this inner product, or they're holding on the state, they don't know the inner product, but when you look at that inner product corresponds to the Hamming weight of this vector that we defined, this XORs. And because we have this promise that Hamming weight is either close to 1/2 n or it's close to 0, then you get this distinction between the two states, so you can identify whether these states are similar to one another or are pretty far apart or close to orthogonal. And then the whole rest of the paper just goes through the error analysis of that. Showing that, in fact, when you apply this projective measurement and you apply the projective measurement for shifting 1, shifting 2, shifting 3, so on, the errors don't accumulate too much. And therefore, you just need some log of 1 over epsilon. It's something like, I think, 1 over 16 n to the 4th is what you have to set epsilon equal to. And you just you get the error down of the shape I function low enough so that the referee can solve the whole shape function with some bounded error. And essentially the idea here is that, I guess the conclusion from all of this is that it's slightly stronger than the paper that Abhishek presented on, in that this protocol is a little bit more restrictive, right? Because there's not this, they can't communicate with one another, and they both have to simultaneously send their messages to this referee. But otherwise, there's still, I guess, Gawinski doesn't mention this, but in other papers, I saw that he brought this up, that I guess like a slightly stronger result would even be if only Alice had quantum information and Bob didn't. Or he also mentions later on this paper, perhaps you consider the case where they don't have the shared entanglement or those sorts of things. So this can be strengthened a little bit more, but Gawinski seemed pretty set that this was a very strong result. And I guess that's it.
Okay, thanks. Yeah, so I guess, any questions for this paper?
Yeah, I have a question. So I'm still trying to understand why it's okay. What about these measurements for the swap test make it okay to keep measuring the state? Like, how do we know that all the information is preserved if we're like repeatedly measuring it?
Mm-hmm. So what you can think of is you can define these measurements as projectors, just these like pi1, pi2 operators that he defines. And applying, one measurement then another is just multiplying these projection operators. So what he does is he does this careful error analysis where he assumes that assume that you should get a 0. What are the odds you get a 1 instead? Or assume you should get a 1. What are the odds you get a 0? And then you can check that for this whole product of projections. And then just take a sum over all those values for, 1 projection, for 2 projections in a row, for 3 in a row, et cetera, to show that the chance that you get an error anywhere down the line is small. So it's not that, yeah, quantum measurements do obviously affect the state that you're in, and you are worried about that destroying the state, but he's very careful to make sure that he's taking the product of these projection operators to account for that. Yeah, I was hoping the error analysis would be as easy as just, taking the, it's a conjunction of random variables and just adding those all up, but that would require sending n independent states, which would obviously ruin the log n result.
Okay, yeah, that makes sense. Thank you.
Okay. Any other questions?
I actually have another, I guess, more general question. Like, what's the intuition behind why these relational problems are like less impressive to show separations between? Like what makes it about functional problems that are so hard versus the relational ones?
Yeah, as I said, I think it's essentially just that, a function is a type of relation, right? So functions are subsets of relations, and then total functions are subsets of, any general function. So the idea is that if you have a result for a relation, that is already a result for, or rather, if you have a result for a function, that also proves a result for a relation. So it's just a, by definition, it's a stronger result.
Yeah, so I guess we didn't discuss relations much so far, but I don't know if we will later. But it turns out to just generally be sort of a more general setting. So if you have so any partial functions can be turned into a relation, and so one way of seeing that, one way to think about it is, so in a relation, what is a relation? It basically just means there's multiple allowed outputs, right? So instead of the function having, let's say, you either have to output 0 if it's a 0 input or 1 if it's a 1 input, maybe there's multiple output symbols, and now there's, for each input there's an allowed set, and you just have to output something within the set. But now consider just a situation where you have a partial function. So, and let's call it, let's say it's a partial Boolean function. So either on every input you either output 0 or output 1, or you say, oh, this is not an allowed input. And of course, on the non-allowed inputs, you don't even have to label them not allowed. You can do whatever you want, right? We only require any algorithm to succeed on the inputs within the promise, on the allowed inputs, basically. We do not require the algorithm to do anything sensible on the inputs outside the promise. So if you have such a partial function, one way to turn it into a relation is to just, and even a total relation basically, is to just say, all right, on the 0 inputs, the allowed output, the set of allowed outputs is just the set containing 0, the singleton set containing 0. On 1 inputs, the set of allowed outputs is a singleton set containing 1. And then on the inputs that are not in the promise, the set of allowed outputs is 0, 1. You're allowed to say either 0 or 1. Of course, the only outputs symbols here are 0 or 1. So that means that the algorithm can just guess, can do whatever it wants, and it will get it right if the input is not in the promise. Okay, so formally we've turned this partial function into a relation, and it's even kind of a total relation. There's no promise anymore. We don't need the promise. But it turns out, especially when you have a large output alphabet, so when you have a lot of allowed output symbols, there's more things you have more kind of richness of design with relations than you do with just partial functions. So it's kind of a strictly more general setting. So it's easier to design a function that will give you a separation that you want. So we'll give you, say, a separation between quantum and classical, query complexity, communication complexity, whatever you want. Yeah, so I guess one kind of slightly annoying thing here, well, about communication complexity in general, is the distinction between all the different types. So there's just a lot of types of communication complexity. So here, well, of course we have, quantum and randomized and deterministic. Okay, of course there's these different types, but then there's two-way communication versus one-way versus simultaneous message passing, which is more restricted than one-way. Basically, it's like it's sort of one-way on both Alice's side and Bob's side at once. They both pass one-way messages to a referee, instead of kind of only Alice passing to Bob. So there's various restrictions on the amount of interaction they can have. Then there's total function, partial functions, and relations. There's that as well. That's another kind of change of setting. Then there's for quantum, whether you allow shared entanglement or not, and for randomized, whether it's public randomness or private randomness. So there's at least these distinctions, and then sometimes people even talk about more of them for whether a distribution over the inputs, like whether here for now in this course we'll basically just deal with worst case inputs. Pretty much always we'll just deal with worst case inputs. So we won't make any further distinctions about average case complexity. But there's also literature on some average case complexities, which is yet another kind of variant of the setting. And of course, there's each of these toggles is independent, right? So you can say, okay, shared entanglement and one-way communication and quantum relations. You can sort of mix and match these descriptors however you want. So you can quickly build up to like dozens of different communication complexities, which is kind of irritating just for kind of housekeeping reasons. But you get used to it. For the most part, there's close analogies to query complexity where things are a little bit simpler. One analogy is that one-way communication or simultaneous message passing, simultaneous message passing. Both of those are sort of different variants of the notion of one-way communication. Of course, the simultaneous message passing is more restricted, but in query complexity, they do sort of correspond to something. They roughly correspond to non-adaptive query complexity. This is, query complexity where you have to kind of decide on all your queries in advance. You don't get to have it like a decision tree of like you see the output to one thing and then you decide on your next query. So you just decide on a batch of queries and make the whole batch at once. And so non-adaptive query complexity for total functions ends up being extremely boring. You basically have to query every bit the function depends on. So you basically have to make n queries unless your function totally ignores some bits. So for total functions, that's the case. But for partial functions, it's really not the case. For partial functions, it's an interesting property of your function, sort of what is the smallest set of bits that can already compute to the function. And that's just deterministic. For randomized, there's a lot of work on non-adaptive randomized query complexity of various partial functions. And then there's quantum, and quantum is also interesting. There is this query analog of it feels roughly like an analog of one-way communication, or maybe an analog of simultaneous message passing, simply because this lack of interaction between Alice and Bob sort of roughly corresponds to a lack of adaptivity of choosing what the next query you're going to make is. It's like, imagine Alice is trying to send things to Bob, or that's a bit like saying, okay, Bob is making queries to Alice's input. It's a little bit similar. So if Alice and Bob are allowed to interact, then Bob can tell her, okay, I saw this. Now, given that I saw your one bit, here's the one I want next, right? It's a bit like making adaptive queries. But if Alice just has to send all her queries without any input from Bob, then it's like Bob is making a non-adaptive, like Bob had to decide in advance which set of bits he's going to want from Alice, basically. So he decided before seeing the inputs, basically he got together with Alice in advance to decide basically what set of queries he's making to her input. So you get a non-adaptive algorithm out of a one-way protocol. It's sort of a similar intuition for simultaneous message passing, except of course with the referee being the person making the queries, this time to both Alice and to Bob at once. The models are kind of they feel similar in flavor. The simultaneous message passing ends up being much harder to have separations in, but in terms of kind of the flavor of them, both feel a bit like non-adaptive query complexity. So I should also mention, I guess, we talk about all these separations. Both of these papers had separations for partial functions. And I guess we mentioned separations for relations, which is a weaker result because relations are a richer framework. So separation for relations is easier to do. You can ask, what about separations for total functions? That would be a stronger result, right? Because it's a more restricted setting. And the answer is that we don't believe you can have them, even for two-way quantum versus two-way classical, but nobody can prove this. So we should be a bit careful because in the notes we already had an exponential separation between deterministic and randomized for total functions. That was the equality function, and that was for just even one-way communication, I guess. The protocol was actually only one way. So there was only an exponential separation there for total functions, even though in query complexity that cannot happen. So we have a polynomial relationship between deterministic and randomized and quantum. But we already know that that doesn't happen in communication complexity because of an exponential separation between deterministic and randomized. So the only question left is, do we also have an exponential separation between randomized and quantum? And here suddenly everybody conjectures no, but it's not clear if we should believe this conjecture. Nobody can prove it. The same techniques that work in query complexity, of course, they don't work in communication, or else they would have shown this false result that deterministic and randomized are polynomial related, which is false in communication but true in query. Right. Another way to think about things is that in the same way that kind of relations are a richer framework than partial functions, like every partial function can be turned into a relation, but not vice versa. In a similar way, communication complexity is richer than query complexity. So if you have a query function, you can kind of lift it to a communication function. If you have a communication function, well, we saw a way to turn it into a query function by kind of just representing the entire communication function as a kind of this doubly exponentially long query problem. However, this conversion is not as good. So this conversion, it doesn't really preserve the communication complexity that much. I mean, it applies a kind of a log to the or something like that to the complexity. It does not preserve the quantum communication complexity at all. It turns the quantum complexity into 1. So it does not preserve any quantum complexity. It's basically a bit of an awkward conversion in many ways. So it's not a very good conversion. It does not generally let you get good query functions or useful query functions out of a communication function. Whereas you can definitely get useful communication functions out of query functions by lifting them. Okay, any other questions about this paper, or any feedback about the notes or the video? All right, maybe I'll maybe have a. Yeah, I should set up some anonymous Piazza thread to solicit anonymous feedback. I feel like nobody ever wants to say anything critical about the notes, so yeah, I should probably do. Well, you always, of course, are free to do that yourselves, right? You could post anonymously on Piazza. I think I have anonymous posting enabled, so there shouldn't be any barrier to doing that. So yeah, just definitely give me feedback in general. So any questions then, or about the week's material, or comments about the material? Okay, well, we are short on time, and that I did kind of want to stop at around 5:30, so because you know, people may have other obligations. So let's just briefly talk about next week. So I'll post 3 readings. Does anybody already know that they're happy to volunteer for next week? It will make things a little easier for scheduling. Otherwise, I'll have to start sending people emails.
I can do next week.
Okay, let me put you down here. All right, thanks. Anyone else?
I'm very happy with the week after next week because I have a seminar on Friday this week.
Okay, sure.
But, I'm not sure if you're taking volunteers for the next week, but yeah.
I can volunteer for next week.
So sorry, I can't hear you. This is Zhang Fei.
Yeah, this is Zhang Fei.
So you're volunteering for next week, did you say?
Yeah. So where can I get the 3 papers, the topics of those 3 papers?
Yeah, so I didn't post the links yet, so I will do it as soon as we close here. I'll post them on Piazza.
So maybe I can check Piazza later and choose one of the papers to present. Is that okay?
Yeah, you want to choose? Sure. So I can put them up if you want to take a look. Okay. I mean, I would put them now in the chat. It's just that I want to finish in like a minute, so I feel like you won't have time to look and get back to me. Okay. Anybody else? All right. So I will choose somebody. There's also people. I think there's 4 people not present. Although I think maybe a couple of them told me that they won't make it. So I'll have to you know, choose somebody kind of offline and announce it. And I guess so Natalie and Zhang Fei, I guess you guys can have first dibs on choosing papers out of the 3 that I post. Although I don't know if it's well, okay, I don't know if it should vary by difficulty that much, in the sense that if you're presenting a harder paper, then you can sort of feel free to go into less detail. You can, you know, the presentation really is, you know, budgeted for 10 minutes or so, regardless of the difficulty of the paper. So, you know, you shouldn't feel like, oh, it's a hard paper, so you have to work really hard. You know, that, I mean, I suppose maybe I don't know how it is on the presenter side. Maybe there's a little bit of that factor, but I hope there is not too much of that factor, and that if you get an easy paper, you may just have to go into a bit more detail on it. Okay. So if there's nothing else, anything else we should talk about, or else we can stop here. Okay, so let me stop the recording, and I'll post the papers right away, and then the kind of content or notes for this week will come a little later, but I'll try to have them as soon as possible this time, and I apologize for doing it slightly late last week. So hopefully I can get that done early. All right. And again, as a reminder, there is QIP this week. So, check it out if you're interested. There's a lot of good talks. Natalie and Zhangfei, is 4:30 next week good for you? Should we set this as the time?
Yeah, it works for me.
Okay. Zhangfei, is that?
Yeah.
Okay, so let's go with that by default. I mean, we should ask the third volunteer as well. Yeah, by default it will be 4:30 again next week. Okay, so I'll see you all then.